Hi, I'm Dr. Jonan Potts, and I'm presenting my poster that I took to RDD this year, and it's on looking at the influence of leucine on internal and external morphology of spray-dried materia. So this is in collaboration with the University of Nottingham. So we want to kind of showcase one of their new techniques called focused ion beam SEM. And one of the things that we really are looking into is that sometimes you spray dry material and it looks very similar from different formulations of that external morphology. So if you see on this figure here, A to D look extremely similar on the outside morphology, but internally that structure might be very different. So as you can see from this top figure, as we're increasing the leucine content from A through to E, the actual internal morphology that goes on there can be vastly different, and you have different porosity levels. So in this project, what we was really doing is just going from a low leucine content formulation A up to a really high leucine content of around 50% of leucine, and that's it, formulation E. And as you can see, it forms a very distinct shell on the outside of the spray dried particle, leaving a kind of porous area in the middle, as that leucine is kind of brushing to the surface under the spray drying process. So we were just trying to highlight how influential focused ion beam could be on looking at spray dried particles of a similar nature to this. So the focused ion beam uses gallium ions to cut a slice out of a spray dried particle, so that you can really understand that internal morphology. It just helps us to kind of build the full picture. If we try to design a spray dried material that wants to go to a pulmonary function or a certain part of the nose, having an idea on how the geometric particle size looks, and then also how that aerodynamic particle size is as well. That internal morphology really helps build the full picture. So to kind of fill out the project a bit more as well, we kind of wanted to have some more information to support what we were seeing. So the theory is that as you increase the leucine content, the more leucine will move to the surface to a point where you get so much at the surface that you break that material and it fragments. So we saw that in formulation E. So looking at TOF sims, we were able to track the leucine content increasing from formulation A up to formulation E. So again, going from 0% to 50% leucine content. We did have one extra formulation in there, which is in F here, and that's where we had the same leucine content of around 12.5% as formulation C, but we also had 1% polysorbate in there, polysorbate 20, and that showed a much higher increase in the leucine at the surface. So that polysorbate seems to help as a porosity effect on the actual internal morphology, and also brings more of the leucine to the surface. So we felt that was quite an interesting effect, and the literature does support that. So it was really nice to actually see that the TOF sims data and the internal morphology kind of support that. We were also then able to do some mapping with the TOF sims as well, so that we could highlight that leucine is coming to the surface. So it really backs up everything that we were looking to show in this project. So overall, this project really was just highlighting that effect of creating a porosity in material, moving the leucine from that low percent to high percent, just to see that shell formation, and that we can have that porosity generated. And using a technique like focused ion beam, it's extremely valuable to understand how those shell formers are actually interacting, and at different percentages how that different thickness of shell and porosity is formed. So we had a great response to the poster. Lots of people are really interested in the images themselves, looking at those spray dried particles at a much closer level than you usually see, and that pie slice really gives you that full picture, the internal and external morphology. And they was talking about ways that they could incorporate this into their projects and their workflows as well, which is great for collaborating with the University of Nottingham. if you click on the QR code or the link below in the video, you'll be able to see how the particles are incrementally sliced so that you really see that full morphology, of that internal morphology. And doing that on multiple samples or multiple particles in a sample really helps you to understand that full picture of how those particles look internally and externally. We've been trying to understand more about how this internal morphology actually looks. So we've been using this in our own projects recently with our clients, and we've had great response. So we thought it'd be a great idea to make this poster to kind of highlight the technique for everyone to see just how interesting it can be to understand that full picture of your particles.